When a research team walks back into a burn zone the summer after a severe fire, they already know roughly what the surface will look like. Blackened trunks, still standing, ash. A landscape that photographs as total loss and that most people assume is exactly that. What that team is actually there to measure is not the surface at all. It is the first few inches of soil underneath it, and in the most severely burned sections of recent Yellowstone area fires. What researchers found in that soil was considerably worse news than anything visible from the air, for a reason almost nobody outside soil science has ever heard of. My name is Marlo Reed. What I want to do today is walk you through what fire actually does beneath the ground in a forest like this. Why the 1988 Yellowstone fires taught a generation of scientists a lesson that may no longer apply, what the soil measurements in recent burn zones are showing, and the uncomfortable question underneath all of it about whether some of these forests are going to come back at all. Let me start with the fire everyone remembers, because the story of 1988 is the reason the current findings are so unsettling. In the summer of 1988, fires burned across roughly 1.2 million acres in the greater Yellowstone area, including close to 800,000 acres inside the park itself. It was at the time the largest fire event in the park's recorded history. The national coverage was apocalyptic. There were serious public conversations about whether Yellowstone had been permanently destroyed, whether the park would ever look like itself again, and whether the Park Service's policy of allowing natural fires to burn had been a catastrophic mistake. And then something happened that reshaped how an entire field of ecology thinks about fire. Yellowstone came back, and it came back fast. Within a few years, the burned lodgepole pine stands were carpeted in seedlings, in some places at densities of tens of thousands of young trees per acre. Wildflower blooms in the burn zones were extraordinary. Elk and bison used the newly opened meadows. The forest was regenerating vigorously without any human intervention at all. The mechanism behind that recovery is genuinely elegant, and it explains why lodgepole pine dominates so much of that landscape in the first place. Lodgepole pine produces two kinds of cones. Some open normally and drop their seed. Others are serotinous, meaning they are sealed shut with a hard resin that holds the seeds inside, sometimes for decades. That resin has a specific melting point, and the thing that melts it is the heat of a passing crown fire. The cone opens in the fire's aftermath and releases seed onto a freshly cleared, nutrient-rich, competition-free seed bed at precisely the moment when conditions favor establishment. The tree does not merely survive fire. Its entire reproductive strategy is built around fire happening on a fairly predictable schedule, roughly every 1 to 3 centuries in that ecosystem. So 1988 became the textbook case. It taught that a severe fire in this forest type is not a catastrophe but a reset, that the system has been running this cycle for thousands of years, and that the correct response is largely to stand back and let it work. That lesson was correct. It is worth stating plainly, because everything I am about to tell you might otherwise sound like I am arguing the opposite. The 1988 recovery was real, and the science behind it holds up. The problem is that the lesson came with conditions attached, and those conditions have been changing. Here's what happens to soil when a forest burns, and this is where the story moves underground. Fire severity in a forest is measured in two separate ways that people frequently conflate. There is fire severity above ground, meaning how much of the canopy and standing vegetation was consumed, and there is soil burn severity, which measures what happened in the ground itself. Those two do not always match. You can have a fire that killed every tree in sight while leaving the soil relatively intact, and that is actually the normal outcome for a fast-moving crown fire. The variable that determines soil burn severity is not flame height, it is duration. How long the ground stayed hot. A crown fire that races through a stand in minutes puts enormous heat into the canopy and comparatively little into the ground, because soil is a poor conductor and heat takes time to move down through it. A fire that settles into heavy accumulated fuel on the forest floor and smolders for hours does something entirely different. That fire drives heat down through the top several inches of soil and holds it there. And that is where the damage that matters actually occurs. The first thing that happens is the loss of the organic layer. The duff, the accumulated needles and decomposed material sitting on top of the mineral soil, is where an enormous amount of a forest's nutrient capital is stored, and where a large fraction of its seed bank sits. A high-severity soil burn consumes that layer completely. What is left is bare mineral soil exposed, with the nutrient reserve and much of the stored seed simply gone as smoke. The second thing is more subtle and considerably stranger, and it is the finding that gives this whole story its weight. When soil heats to a certain temperature range, organic compounds in the duff layer vaporize. Those vapors move downward through the soil profile into cooler layers below, where they condense and coat the individual soil particles with a waxy organic film. The result is a layer of soil, typically an inch or two beneath the surface, that has become water repellent. Hydrophobic. Rain falling on that ground soaks into the top inch and then hits an invisible waxy barrier and stops. That is the finding, and it is not a new discovery. Soil hydrophobicity following severe fire has been documented in fire science for decades. What is new is how frequently and how extensively researchers are measuring it in burn zones that, by the 1988 model, should have been recovering. Water that cannot penetrate has to go somewhere, and what it does is run across the surface, carrying the exposed ash and loose mineral soil with it. The erosion rates measured in severely burned watersheds after the first significant rainfall event are dramatically higher than in unburned terrain, sometimes by orders of magnitude. Debris flows and steep burn drainages are a recognized post-fire hazard specifically because of this mechanism. So the soil that survived the fire itself frequently does not survive the first heavy rain afterward. It ends up in the creek. That connection between what a place appears to be on the surface and what is actually happening underneath it is exactly why I put the uncovered files together. Some of these cases carry more documentation, more sourcing, and more genuinely unresolved material than a single upload has room for, including the findings still working their way through peer review where I have to stop short on camera. It is linked in the description. Now, back to the soil, because losing the seed bank and losing the ground are only the first two problems, and the third one is the one researchers find hardest to talk about publicly. Beneath a healthy conifer forest, the tree roots are not operating alone. They are connected to an enormous network of fungal filaments called mycorrhizae, and that relationship is not incidental to how the forest works. It is fundamental. Mycorrhizal fungi colonize tree roots and extend far out into the soil, dramatically increasing the volume the tree can draw water and nutrients from. In exchange, the tree supplies the fungus with sugars from photosynthesis. It is one of the oldest and most widespread partnerships in terrestrial life, and conifers in particular are heavily dependent on it. A seedling attempting to establish in soil without appropriate fungal partners is at a serious disadvantage, and in some conditions cannot establish at all. High severity soil burns damage those fungal communities substantially. The fungi live in exactly the upper soil layers that get cooked, and unlike the trees, they do not have a serotinous cone waiting to reseed them. Recolonization happens from surviving patches, spores, and the edges of the burn, and how fast it happens depends heavily on how large the severely burned area is. That last point is the hinge of this entire story, and it is worth slowing down for. In a patchy burn, one where high severity areas are small and interspersed with lightly burned or unburned ground, recovery is fast for exactly the reasons Yellowstone demonstrated in 1988. Seed blows in from surviving stands nearby. Fungal networks spread outward from intact edges. Soil erosion is limited because there is unburned ground to catch it. The unburned patches act as reservoirs, and the burned areas recover from the outside in. In a large, uniformly high-severity burn, all of that changes. The distance from the interior of the burn to the nearest surviving seed source may be measured in kilometers. Wind-dispersed conifer seed does not typically travel that far in useful quantities. The fungal networks have no nearby edge to spread from. There is no unburned ground to buffer the erosion, and so the interior of a very large severe burn can fail to regenerate as forest at all, converting instead to grassland or shrubland, sometimes for a very long time. Researchers have a term for this, reburn, when a young stand burns again before it has reached reproductive maturity, is one specific pathway to it. Lodgepole pine begins producing cones somewhere in the range of a couple of decades after establishment, and serotinous cone production takes longer still. If a stand that regenerated after 1988 burns again at age 30, There is no seed bank to release because the trees had not yet built one. That is the scenario that has moved from theoretical concern to documented observation across the western United States over the past 2 decades. Now let me connect this back to why the 1988 lesson came with conditions. The lodgepole system evolved under a fire return interval measured in 1 to 3 centuries. Everything about the strategy assumes that gap. The tree has that long to establish, mature, and accumulate a bank of sealed cones before the next fire arrives to open them. Shorten that interval enough, and the strategy stops working, not gradually, but as a threshold. Either the trees had time to build a seed bank, or they did not. Fire seasons across the western United States have lengthened substantially over recent decades, and the area burned annually has increased. The scientific literature on this is extensive, and the direction of the trend is not seriously disputed. Warmer temperatures, earlier snow melt, longer dry seasons, and increased vapor pressure deficit all contribute to fuels that are drier for longer stretches of each year. Longer and more severe fire seasons mean more fires, larger fires, and more of them burning at high severity across large contiguous areas. Every one of those factors pushes toward exactly the conditions where the 1988 recovery model breaks down. So the researchers walking into recent burn zones are not measuring soil because they expect it to be interesting. They are measuring it because the soil is where you find out which kind of recovery you are going to get, years before the surface tells you anything. Let me describe what that fieldwork actually involves, because it is considerably less dramatic than the findings. Soil burn severity mapping combines satellite imagery with ground verification. From orbit, researchers can identify burn severity classes across an entire fire perimeter, but those classifications need checking against reality, which means field crews walking transects across the burn and taking measurements at fixed intervals. The hydrophobicity test itself is almost comically simple for something with such serious implications. You clear the surface and you place a single drop of water on the soil, then you time how long it takes to absorb. On normal soil, it disappears almost immediately. On water-repellent soil, the drop sits there, beaded, sometimes for minutes. Crews repeat this at multiple depths by scraping down in increments, mapping where the repellent layer starts and how thick it is. Alongside that, crews measure the depth of remaining organic material, assess root damage in the upper profile, take samples for laboratory analysis of nutrient content and microbial community composition, and record the ash color and depth which correlates with the temperature the ground reached. None of this is glamorous work. It is done in heat and ash that gets into everything, in a landscape that smells strongly of burned resin for months afterward, on foot, across terrain full of standing dead trees that fall without warning, and that crews have to constantly assess overhead. Snag hazard is one of the genuine dangers of post-fire fieldwork, and it is why teams frequently work in high wind conditions only under specific protocols, or not at all. What the accumulated measurements from recent severe burns keep showing is a consistent pattern in the highest severity areas. Organic layer largely consumed. A water repellent layer present at shallow depth across substantial portions of the burn. Fungal community composition significantly altered, and distance to viable seed source in the interiors of the largest burns, well beyond the range at which natural conifer reseeding reliably occurs. Any one of those is a recoverable setback. The combination is what changes the projected trajectory. I want to be careful here, because this is exactly the point where a story like this can tip into overstatement, and the actual science is more measured than the headline version. Not every severe fire produces significant soil hydrophobicity. The effect depends on soil type, moisture content at the time of burning, the specific vegetation, and the temperature and duration of heating. Sandy soils tend to develop it more readily than clay-rich soils. It is common, and it is well documented, and it is not universal. It also does not last forever. Water repellency in burned soils typically breaks down over a period ranging from a single season to a few years, as the waxy compounds degrade and freeze-thaw cycles and biological activity disrupt the layer. The window during which it matters most is the first 1 or 2 rainy seasons after the fire, when the ground is bare and the layer is intact. That is precisely when the erosion happens, which is why post-fire emergency stabilization work is so time-sensitive. Similarly, mycorrhizal communities do recover. The question is how fast and from where, and that returns to the patch size problem rather than being a permanent loss. And forests do still regenerate after severe fire in a great many cases, including in the Yellowstone region. The concern is not that regeneration has stopped. It is that the fraction of burned area failing to regenerate as forests is measurably increasing, and that the mechanism driving that increase is not something that reverses on its own. There is one more piece to this that deserves its own attention, and it involves a tree most people have never heard of. Whitebark pine grows at high elevation across the greater Yellowstone area and much of the northern Rockies. It produces large fatty seeds that are a genuinely important food source for a range of wildlife, including grizzly bears, which is why it gets discussed in conservation contexts far more than its commercial value would suggest. Whitebark pine is in serious trouble for reasons that have almost nothing to do with fire. An introduced fungal disease called white pine blister rust has been killing it across its range for decades. Mountain pine beetle outbreaks, which have expanded in part because warmer winters no longer reliably kill overwintering beetles at high elevation, have killed enormous numbers of mature trees. The species has been assessed as threatened under the Endangered Species Act. Now add fire to a population already reduced by disease and insects. Whitebark pine does not have serotinous cones. Its seeds are dispersed almost entirely by a single bird species, Clark's nutcracker, which caches seeds in the ground and fails to retrieve some of them, which is how the tree reproduces. That relationship is remarkable, and it is also a bottleneck. If nutcracker populations decline because there are not enough cone-producing trees left to make the caching behavior worthwhile, the dispersal mechanism weakens exactly when the tree most needs it. Fire in already thinned whitebark stands, combined with damaged soil and a struggling dispersal partner, is a compounding problem rather than an additive one, and it is one of the clear examples of why post-fire recovery cannot be assessed by looking at any single factor in isolation. So what is actually being done about any of this? More than most people would assume, and less than the scale of the problem calls for. Emergency post-fire stabilization teams assess severely burned watersheds within days of containment specifically to identify areas where hydrophobic soil and steep terrain create debris flow risk to downstream communities and infrastructure. That work is genuinely urgent, genuinely effective at preventing loss of life, and operates on timelines measured in weeks. Longer term, land management agencies conduct post-fire regeneration surveys to identify areas that are failing to reseed naturally, and in some cases plant seedlings directly. Replanting a burned forest is expensive, labor-intensive, and constrained by seedling nursery capacity, which is a genuine bottleneck across the western United States that gets very little public attention. There are simply not enough seedlings grown annually to replant the acreage burning annually, and that gap has been widening. There is also active research into which seed sources to use, which is a genuinely difficult question. Planting seedlings adapted to the climate of the past few decades into a site that will experience a warmer climate over the coming century is a known problem, and assisted migration of seed sources is an area of ongoing and somewhat contentious research. And there is the fuels question, which is where this becomes politically complicated in a way I want to describe accurately rather than take a side on. A century of aggressive fire suppression across the American West allowed fuel to accumulate in many forest types well beyond historical levels. In fire-adapted forests that historically burned frequently at low severity, that accumulation has genuinely contributed to fires that burn hotter and more severely than they would have historically. Thinning and prescribed burning in those forest types is broadly supported in the scientific literature as a way to reduce severity. Where it gets complicated is that not every forest works that way. High elevation lodgepole systems like much of Yellowstone historically burned infrequently and at high severity. That was always the pattern. Suppression did not fundamentally alter the fire regime in those stands the way it did in lower elevation ponderosa forests, and treatments designed for one system do not necessarily help in the other. Applying a single policy across forest types that behave differently is a real risk, and researchers who study this are consistently clear that the appropriate treatment depends heavily on the specific forest. I keep coming back to one thing as I work through all of this. The 1988 fires produced a genuine and important scientific lesson, and the lesson was reassuring. Fire is not the enemy. The forest knows how to do this. Stand back and let the system work because it has been working for thousands of years. That lesson was built on a landscape where fires arrived roughly every 1 to 3 centuries, where burns were patchy enough that unburned ground served as a reservoir, and where a tree that had spent 150 years quietly accumulating sealed cones would be waiting when the fire came through. Every one of those conditions is a variable rather than a constant, and the variables have been moving. What the soil measurements and recent severe burns are documenting is not the failure of that lesson, it is the boundary of it. The conditions under which the reassuring version holds, and the conditions under which it stops holding, and the fact that more of the landscape is crossing from the first category into the second each decade. The surface of a burn zone tells you almost nothing about which side of that line a particular place has landed on. 2 burns can look identical from a helicopter, blackened trunks and ash in every direction, and one of them will be carpeted in seedlings in 4 years, while the other converts to grassland for the next century. The difference is in the soil, in the fungal communities, in the distance to living seed, and in whether the trees that burned had lived long enough to leave anything behind. That is why teams walk those transects with a squeeze bottle and a stopwatch, putting single drops of water on burned ground and counting the seconds until it soaks in. It is unglamorous work that answers a question the landscape will not otherwise reveal for decades. And the answer, in the most severely burned interiors of the largest recent fires, has increasingly been that the drop just sits there. There is a version of this story that is straightforwardly grim, and I do not think that version is accurate. Forests are still regenerating across most burned acreage. The Yellowstone landscape today is not the ruined place people feared in 1988. And the ecological understanding that came out of those fires genuinely improved how public land is managed. Post-fire stabilization saves lives. Replanting works where it is funded and executed. Fungal communities recolonize. Water repellency breaks down. But there is another version where the specific combination of longer fire seasons, larger high-severity patches, shortened return intervals, and damaged soil is pushing an increasing fraction of this landscape past the point where the reassuring 1988 story applies, and where the transition from forest to grassland is not a temporary phase, but a durable change on any time scale that matters to people currently alive. Both versions are drawing on the same measurements. The disagreement is about proportion and pace rather than mechanism, and it is being worked out in the literature right now. What I find genuinely difficult to sit with is the timescale mismatch. A lodgepole pine needs a century or more to build the seed bank that lets its stand survive the next fire. The interval between fires in parts of the western United States has been contracting over decades. The tree cannot adjust its reproductive strategy on that schedule. Nothing in its biology allows for it. That is the whole problem stated as plainly as I know how to state it. A system built around one time scale is being asked to operate on a different one, and the mismatch is not visible on the surface. It is in the soil, in the seed bank that burned before it was full, and in the fungal networks that have no intact edge nearby to spread back from. Researchers returned to those burn zones expecting to document a recovery they had watched happen before. What the ground told them in a great many places was that this one is going to go differently. I am Marlowe Reed. If the quiet mechanisms sitting underneath ordinary landscapes are why you keep coming back to this channel, subscribe, because the ground under a great deal of this country is doing things most of us were never told about, and I intend to keep working through it. I will see you in the next one.